We're moving on to 12.4, integrated rate laws. Here we're going to explain the form and function of an integrated rate law, perform integrated rate law calculations for zero, first, and second order reactions, define half-life and carry out related calculations, and identify the order of a reaction from concentration time data. So far, we have really only talked about the relationship between concentration and rate. We can integrate a rate law with respect to time, and this gives us a concentration time relationship known as an integrated rate law. We are not going through integration that is calculus and chemical engineering kinetics or grad level kinetics, so do not stress about it. Just take my word for the equations that we're going to go over. So this relationship itself depends on the order of the reaction, zero, first, second, etc. Zero, first, and second being the most common, the ones that we're going to talk about. And we're also going to look at half-lives and derive some equations. So if we have a first order reaction, we have some type of A becoming products, and our rate equation is something like some K constant times our concentration of A. If we were to integrate this with respect to time, we get the natural log of A naught. Okay, so A naught is the initial reactant concentration, A0, A naught, however you want to say that, divided by the concentration of A at some time t, at whatever your present time is. And that is equal to your rate constant times your time. Now we can actually put this in an integrated rate law. We can put this into a linear form. And the way we do that is we multiply both sides, or we multiply both sides. And this ends up simplifying down to the natural log of A at time t is equal to negative kt plus the natural log of A naught. So A at time t, that concentration can change, whereas A naught, that initial concentration, stays the same. So we want to solve for this natural log of AT because that, again, that changes over time. So to do that, if we were to separate this natural log here, when you divide natural logs, you can also rewrite them as subtraction. So we can also say the natural log of A naught minus the natural log of AT is equal to KT. So then we subtract both sides by natural log of A naught, and we get negative natural log of AT equals KT minus natural log of A naught. And then we multiply everything by -1 to get rid of this negative sign to get our final form. The natural log of AT equals negative KT plus natural log of A naught. Now you may not see that this is a linear equation here until we kind of look at this. Y equals mx plus b. So our points on the line, the x is on our line, the x-axis is represented by our time, t. So if we're plotting our data for a first order reaction, or first order rate law, time is on the x-axis. And the y-axis is the natural log of our reactant. And then the slope of our line, the negative slope, is equal to our k. So we'll get a line that kind of looks like this. Okay, so the slope, so the negative slope, okay, is equal to k. And your y-intercept is equal to the natural log of A naught. Pretty cool, right? So you can plot this data. Let's say you're in the lab and you're recording your concentrations at certain times. You can plot this data for a first order reaction, and you get a straight line that looks like this crappy graph I drew, and you could take the equation of that line and get your slope, the A naught concentration, and now you have an equation for your line to predict your different concentrations at various times. Now, a couple things to note. The amount of the reactant, your A, does not have to be molarity. The brackets tend to imply molarity, but you can use mass, you can use number of molecules or atoms, or grams per liter concentration, or partial pressure if we're looking at gases, assuming volume and temperature are constant. So let's look at an example. We are told the rate constant for the first order decomposition of cyclobutane, C4H8, at 500 degrees Celsius is 9.2 times 10 to the negative third inverse seconds. And we want to know how long it's going to take for 80% of a sample to decompose. So let's first go ahead and write our equation. And the natural log of A naught divided by AT, oops, is equal to KT. Now we're looking for T here. And the other thing is we can go ahead and say that A naught is equal to X. Okay. And we also know that 80% of our sample is decomposed. So because of that, we know then that AT is equal to 20% of X because 80% is gone. So AT is equal to 0.20X. We don't even need our actual concentrations here because of this ratio. Watch what happens. The natural log of X over 0.20X, our X's divide out, is equal to KT. So T now is equal to K divided by the natural log of 1 over 0.2. And that gives us 9.2 times 10 to the negative third. Oops, I'm sorry. Backwards. T is equal to the natural log of 1 over 0.20 divided by K. There we go. And that's why you keep an eye on units. So I started to write K and went, wait, these are inverse seconds. 1 over inverse seconds will give us seconds, and that's what we want here. So 9.2 times 10 to the negative third inverse seconds. So that's 1 over seconds, which is why we're going to have seconds in our final answer. So if we want to go ahead and calculate the natural log of 1 divided by 0.2, that's the natural log of 5, and we can go ahead and write this as 1.61 or 1.609, really whatever you want to, however you want to write it. Time now then is 1.7 times 10 to the second seconds. 10 to the second seconds. Blech. Okay. So there's our first example, just using the regular rate law, not even having to use the linear form, which you still could. It's all the same. You'd still get the same answer. But yeah, there you go, solving for T. So our next example, we are told that we want to look at the data in figure 12.2. This is from earlier in the chapter, where we were first looking at change in concentration, delta concentration over delta T. And we want to show that it can be represented by a first order rate law by graphing the natural log of H2O2 versus time, and then figure out the rate constant from the data. So looking back, we're given a table. We have these different trials, and they gave us a time in hours, concentration of H2O2 in molarity. Okay, so we have trials 1, 2, 3, 4, and 5. Time 0, 6, 12, 18, and 24 hours. Our concentration 1.0, 0.5, 0.25, 0.125. I'm kind of ignoring the extra zeros. I know I shouldn't because sig figs, but There's only so much writing I want to do in a day, you know? Okay, so because this is first order, we want to prove it's first order. That means we need to take the natural log of our hydrogen peroxide concentrations. So we need to add now a new part of this table, natural log of H2O2. So we're going to take the natural log of the column next to it. If you are an Excel whiz, you could set up Excel spreadsheet and tell it to do that, and you click and drag. Okay, so 0 for natural log of 1, the natural log of 0.5, you get negative 0.693, negative 1.386, negative 2.079, and negative 2.772. So now I've got a little grid here. I'm going to draw my axes. Please don't come for me because I suck at drawing straight lines. Our time is going on the x-axis, and this is in hours. So here's 0 hours, 6, 12, 18, and 24 hours. And the y-axis is our natural log of H2O2. Okay, so at the top up here is 0, and then negative 1. It's not usually good to do what I'm doing here, so do as I say, not as I do, but I don't have room to do it on the outside. 0, negative 1. Oh, no, actually, no. I want to do it here. 0, negative 1, negative 2, negative 3. So that means on my y-axis here, crossing at 0 is negative 4. It doesn't matter where you put your axes. So you don't always have to have your axes going at 0, 0. Okay? So at the point where at time 0, my concentration of H2O2, or sorry, my natural log of H2O2 is 0. So that means I have a point right up here at the tippy top. At 6 hours, my natural log is negative 0.693. So that is right about here, almost 0.7. At 12 hours, we have negative 1.386. So I'll put that right about there. At 18 hours, we have negative 2.079, about there. And at 24 hours, we have negative 2.772, right about there. So now we're going to go ahead and connect our points, if my pen will let me. That was a terrible straight line, but it's as good as I'm going to get, because I suck at that. And you notice we have a nice straight line. Because it's a straight line, that tells us this, yes, this is first order. So then the next thing to do, we want to figure out our rate constant. So our rate constant, so if you remember from the general linear equation, the natural log of AT is equal to negative KT plus the natural log of A naught. Now here we already knew A naught, since it was there at 0 time, we had concentration of H2O2 of 1 molar. But if we didn't, we could look at the graph and we would get that, and we'd see, oh, look, it crosses here. So the natural log of A naught is equal to 0, and then you do e to the 0 power equals A naught equals 1. So a lot of times when you do this type of work too, you do a linear regression using Excel. I will probably make a separate video in the very near future, probably put it out sometime this week, to kind of show you how to use Excel to do this type of thing. It makes life a lot easier, especially when you're dealing with data that is not perfect. In this case, we make a perfect line, but if you were doing this experiment or something like it in a lab, your line's not going to be perfect. So that's where having a computer to plot the best fit line comes into play. Nonetheless, your computer would give you your equation, your y equals mx plus b, and then you could look at it and go, boom, m, that's my slope. Now I know my k. But here, we can't quite do that, so we just want to get the slope of this graph, and in this case, we're just going to go ahead and use some of our data points. And for here, let's just use trial 1 and trial 5. Those are both points on a line. Remember, with the slope of a line, it doesn't matter what 2 points you choose as long as they're on the line. So the slope, Rm, k is equal to the change in y over the change in x. So that means change in our natural log. So negative 2.772 minus 0 divided by the change in x, 0 minus 24 hours, sorry, not 0, 24. I was like, wait, minus 0. So this gives us negative 0.116 inverse hours. Okay, because on top, natural log does not have units, but on bottom, those are both hours. Okay, but remember, the slope of our graph is equal to the negative k. So that means multiply this times negative 1. K now is equal to 0.116 inverse hours. Now we have our rate constant for our reaction. And here's a prettier graph of what I just drew very badly. So we're kind of skipping, we're going to do a little back and forth in this section. Your book goes through the 3 basic rate laws and then moves on to half-life, but I like doing it, the half-life with each type, with each order of reaction, so that way, you know, it doesn't get as confusing. So we're going to talk about half-life now. Half-life of a reaction is the time it takes for 1/2 of a given amount of reactant to be consumed. So for a first order reaction, your half-life is equal to the natural log of 2 divided by k, and which is 0.693 over k. So the way that that we find this is we are solving for t from our linear equation. And one thing that we need to note here is that AT is equal to 1/2 A naught. And actually, it's better to do this using the regular form of the equation, using the natural log of A naught over AT equals KT. So now we know, again, so after a half-life happens, we have half of our initial concentration. So we can take that and substitute that into our equation. So we get the natural log of A naught divided by 1/2 times AT, or sorry, 1/2 times A naught equals KT. So our A naughts cancel. 1 over 1/2 means we have the natural log of 2 is equal to KT, and we call this KT 1/2 since we're talking about a half-life here. And we get T 1/2 equals the natural log of 2 divided by K. It's up to you if you want to write it as 0.693 or natural log of 2. Doing a natural log of 2 is a little bit more exact because you're not rounding to just 3 decimal points, but again, it does not matter. So that is the half-life for a first order reaction. We're going to look at the equations for second order and 0 orders later. But first, an example. Also, one thing to notice for a first order reaction, notice there's no concentration in this equation. It is independent of the initial concentration of reactant. It does not matter how much reactant we have, our half-life doesn't care, okay? So let's look at an example. We want to calculate a first order rate constant using half-life. We're given this decomposition of hydrogen peroxide in water at 40 degrees Celsius, and figure 1212 is what you see below. We're given these concentrations changing over time, and it's telling us seconds elapsed as well as hours elapsed. This color intensity is really just showing giving a visual representation of the concentration of hydrogen peroxide at the different times, but it's actually colorless. So don't try to put hydrogen peroxide from the bathroom or whatever in water and expect it to turn green. Sorry. All right. So when we look at this, we're starting with 1 molar. And we see that half of it is gone down to 0.5 molar in 6 hours. And you can also look at if you're going from 0.5 to 0.25, that's also decreasing by half. That is a difference of 6 hours. So notice every single step here is a difference of 6 hours, and we're going down by half of our concentration. So we know that our half-life is equal to 0.693 divided by K. But in this case, we want to solve for K. So K is equal to 0.693 divided by T1 half. And we know our T1 half is 6 hours. And instead, though, we're going to go ahead and use seconds. We know our T1 half is 2.16 times 10 to the 4th seconds. So you could use the hours if you wanted to, unless it tells you what units to do. I don't care if I'm on an exam and I don't tell you units, you can decide. I really don't care. All right, 0.693 divided by 2.16 times 10 to the 4th seconds. And this gives us 3.21 times 10 to the negative 5th inverse seconds for our K. And there we go. That is our K constant. All right, now that we have talked about first order reactions, let's talk about second order. So the second order integrated rate law, if we have some A going to products, our rate is something like K times concentration of A squared. This is an overall second order. And we integrate this with respect to time. We get 1 over A times T is equal to KT plus 1 over A naught. And if we want to go ahead and figure out the equation for its half-life, okay, I've given you the equation, but for my curious people, let's go ahead and talk about this. We know at a half-life that the concentration, so at a half-life, the concentration of AT is going to equal 1/2 the concentration of A naught. Okay, so we can go ahead and substitute that in, and we get 1 over 1/2 A naught. And I'm going to bring this guy, put it on the side, minus 1 over A naught equals KT. And this simplifies down to 2 over A naught minus 1. Okay, 1 over 1/2 equals 2. So that's now 1 over A naught is equal to KT 1/2. So then T half is equal to 1 over K times A naught. Okay, we divided both sides by K. So now you can see how we got that equation. Now notice for this half-life that the second order reaction does depend on the initial concentration of reactant. So now let's go ahead and look at some examples. Starting with looking at the integrated rate law for second order reaction, we're told that the reaction of butadiene gas to yield C8H12 gas is described by the balanced equation there. This is called a dimerization reaction, and we're told it is second order with a rate constant equal to 5.76 times 10 to the negative second liters per mole per minute under certain conditions. If the initial concentration of butadiene is 0.2 molar, what is the concentration after 10 minutes? So let's go ahead and first write our integrated rate law. And we have 1 over AT is equal to KT plus 1 over A naught. And we were told A naught already. Okay, so A naught is equal to 0.200 molar. It's good to write down what we know. K is 5.76 times 10 to the negative second liters over mole times minute. And the other thing that we know is that our time is equal to 10 minutes. So we're solving for AT here. We know everything else. We know K, we know T, we know A naught. I like to solve things in terms of variables first. At least let's get that we don't really have anything to do. So we can go ahead and just plug in our numbers and then we'll divide everything by 1. So now plugging and chugging, we get 5.76 times 10 to the negative second liters per mole minute times our time of 10 minutes. And you could see the minutes there cancel. And we're adding to this 1 over 0.200 inverse moles. Sorry, 1 liter over. So molarity, remember, is moles over liter. So when you have 1 over A naught, then that means you have 1 over moles over liters, which gives you liters over moles. There we go. And look, those units end up matching up. So we can add that to the 5.76 times 10 to the negative second. So that gives us, now when we add those together, we get 5.58 liters per mole. Liters over mole is 1 over AT. So now we need to go ahead and do 1 divided by everything, or put everything to the negative 1 power, so we can get AT in that numerator. So AT then is equal to 1.79 times 10 to the negative first moles per liter, or molarity, molar. So after 10 minutes, there's 0.179 moles per liter of butadiene remaining. So now let's look at another example. In this one, we're going to be doing some graphing, so you get to see my beautiful sketching again. We're given some data for the reaction that we just looked at, and we want to make some plots to identify if it's first or second order, and after we determine that, figure out the rate constant. So we're given trial numbers, some times, and concentration. We cannot just graph concentration versus time. So we need to do some transformations of our data before we can plot it. So we're going to have a first order graph and a second order graph. Spoilers. So remember, like we talked about with the first order reaction, we need to take the natural log of our C4H6. So we take the natural log of each one, we get, oops. Oh yeah, yes, okay. Negative 4.605, negative 5.289, negative 5.692, negative 5.978, and negative 6.175. So if this were first order, let's go ahead and now plot this. Remember, time is on the x-axis, and the natural log of C4H6 is on the y. So we have terms of seconds, so we have 0 seconds. We're just going to go ahead and make each of our lines here is 1600 second difference. 3200, 4800, and 6200. For our y-axis, these aren't the prettiest numbers to deal with, so we're going to go ahead and go start here at 4. This will be 4.5. 5. Actually, we'll start at 4.5. That'll be better. So 4.5. This is 5. This is 5.5. 6. This is 6.5 up here. All right. So at time 0, the natural log of C4H6 is equal to negative, oops, I did it backwards. Duh. Don't be like me, children. 6.56, 5.55, 4.5. There we go. Remember, these are negatives. So we're below the x-axis here. All right. At time 0, our natural log of C4H6 is negative 4.605. So that's going to be right around here. And then at time 1600 seconds, we have negative 5.289. So put that right about there. Then 3200, negative 5.692. About there. Oops. Let me move this down a little bit. Right about there. Okay, at 4800, we have negative 5.978. That's basically 6. And at 6200, we have negative 6.175. So if you look at this, that is not a straight line. That is a curved line. So that tells us that no, this is not a first order reaction. Because if it was first order, we would get a linear fit that we could then put on a graph and go from there. So let's now look for a second order. Remember, for the second order graph, our reaction, or our equation, excuse me, it was 1 over AT is our y equals KT. So there's mx plus 1 over A naught B. So our y data is 1 over AT, our slope is K, our x data is T, and our y-intercept is 1 over A naught, aka B. So now we need to do 1 over AT for all of our data. So in this case, 1 over the concentration of C4H6. So we do that, the concentration at time 0, 1 over 1 times 10 to the negative second is 100. At 1600 seconds, we have 198, and then 296, 395, and 481. So now let's kind of get this set up. 0, 1600, 3200, 4800, and 6200, and okay, 100, 200, 300, 400, 500. So at time 0, 1 over C4H6 was equal to 100. So that's right here. At 1600 seconds, we have 198. 3200 seconds, we have 296. 4800 seconds, we have 395. And at 6200 seconds, we have 481. So that's looking pretty straight. And we can go ahead and connect those points. And we see we have a nice straight line. So yes, this is a second order. And now we want to go ahead and use this data to find our K constant. So that's the slope of our line. So we're going to go ahead and take 2 points from it. And let's just go on and use time 0 and time 6200. Okay. So the slope, which is K, is equal to the change in Y over the change in X. So the change in Y, that's going to be the 1 over C4H6. So we have 481 minus 100 divided by 6200 minus 0. And so these are 1 over molar, so inverse molar on top, seconds on bottom. So then our units for K are inverse molars, inverse seconds. So then we get that K equals 0.0614 inverse molar, inverse seconds. And there we go. And there's those graphs drawn way better than I could do. I'm an Excel whiz, though. I can make beautiful graphs in Excel. All right. And we already talked about half-life for second order, so now we're going to talk about zero order reaction. So for this reaction, you have some A going to products, but your actual rate, that A is to the 0 power, so your rate is just equal to K. If you were to integrate this with respect to time, you get that AT is equal to negative KT plus A naught. So that's a really nice linear one, right? You can see that right away. Y equals mx plus b right there. Now let's go ahead and get the half-life. So remember at t half, AT is equal to 1/2 A naught. So now we have 1/2 A naught is equal to negative KT plus A naught. Subtract A naught from both sides. And then you get negative 1/2 times A naught equals negative KT. Multiply both sides by -1, or actually by -2, because then we get A naught by itself. So now A naught is equal to positive KT. Oh, wait. We don't want to divide by A naught. We're solving for T here, Ash. Duh. T 1/2. I don't know why I keep doing that. So we want to get T 1/2 by itself. We're going to divide both sides by negative K. So T 1/2 then is equal to -1 over 2K times A naught, or you could just say A naught over -2K, however you want to put that. So that's how we get our half-life equation. So in this one, just like with the second order, we do rely on the initial concentration of reactant. So second order and zero order reactions they depend on the initial concentration of reactant to find your half-life, whereas first order does not depend on it. So let's go ahead and look at an example. So here's a plot. We want to graphically estimate the zero order rate constant for ammonia decomposition at a tungsten surface. So tungsten is W. So there's two graphs there. We want this guy, that's decomposition on W, that's tungsten. So we know from the equation for a zero order that AT equals negative KT plus A naught. So the rate constant is equal to the slope. So we're going to go ahead and choose 2 points on this graph. And so looking at it, let's see, at 1,000 seconds, we're just going to go ahead and do this. 1,000 seconds, this is approximately 1.5 times 10 to the third molar. Okay, so this point, well, that was terrible, but this is at point 1,000, 1.5 times 10 to the negative third. And then here we have times 0, and that's about 2.8 times 10 to the negative third molar. Okay, so there's our coordinates that we're going to use to get our slope. Okay, so K is equal to the negative slope, so K equals negative slope, negative M, so which that equals negative times change in Y, 1.5 times 10 to the negative third molar minus 2.8 times 10 to the negative third molar divided by 1,000 seconds minus 0 seconds. So this gives us 1.3 times 10 to the 6 molar inverse seconds. Boom, now we found K. I know zero orders are so nice, aren't they? And then this is just that graph again, but it's showing you how ammonia can be decomposed either on tungsten, which is zero order, or on a quartz surface, which is a first order reaction. But you can also get a good idea of the difference if you were to try to graph concentration versus time for a first order. Notice it's not a straight line. It may kind of look like it at first, but it is not. So our next question, we want to know the half-life in milliseconds for the butadiene dimerization that we talked about in example 12.8. So this was a second order reaction. So that means that our T1/2 of a second order reaction is equal to 1 over K times A naught. And so from that reaction, we had solved for K, I believe, and we got 0.0576 liters times inverse moles times inverse minutes times A naught, which is 0.200 molar, aka moles per inverse liter. So we can see our liters go away here, our moles go away, and we're left with 1 over inverse minutes, which gives us minutes. So that gives us 0.0115 minutes, but we want milliseconds. So let's do some conversions. 0.0115 minutes. And we know that there are 60 seconds for 1 minute. So let's say you don't know how to go from minutes to milliseconds. Okay. And now we can go from seconds to milliseconds. Milli means 1,000. There's 1,000 milliseconds for every 1 second. So we can see minutes cancel, seconds cancel. We're left with milliseconds, and we get 690 milliseconds.